word radical is used to describe something which is a bit different. This is Cycroludes frictus, a radical fish. This graphic shows 4 types of chemical species that can bond, forming chemical compounds. On the left is a positive ion called a cation. It has lost its single valence electron to another element. Second, we have a negative ion called an anion. It has taken 2 electrons from another element to fill its outer shell. These first and second elements will bond, forming anionic compounds. The third element has a half-complete outer shell. It prefers to share its electrons with other atoms, forming molecules. On the right is an example of a radical anion. This exotic chemical is one species found in your bones. This is the sulfate ion that old chemistry teachers call the sulfate radical. All radicals carry a net charge. This is an anion because it is negative. Its valence or combining power is -2. Sulfate is a common radical formed when sulfuric acid forms salts with metals. It is found on its own when dissolved in water, or in crystal form when combined with metal ions. Radicals are more stable than the atoms that form them. Like all chemicals, they can be made to react further. Radicals are called polyatomic ions because they contain more than one atom. This radical contains 4 oxygens surrounding a sulfur as piggy in the middle. Radicals have structure. This one is a perfect pyramid called a tetrahedron. Others are pyramidal, bent or linear. Radicals contain a number of covalent bonds where electrons are shared between atoms. Each bond line represents 2 shared electrons. A few chemical salts call radicals molecular ions. Here we have 2 nonmetal atoms, oxygen and chlorine. The outer shell valence electrons are shown. Both have an almost complete outer shell, which they are desperate to fill with 8 electrons. One way they can do this is to share 2 common electrons. But they need an extra electron from outside to do this. They end up forming a quite reactive radical called the hypochlorite ion that has a linear shape. The chlorine provides 1 electron to be shared, shown in green. The red electron comes from the metal that has combined with the radical. The oxygen provides no electrons in the structure. The 2 shared electrons form a single covalent bond on the right. The net charge of the radical is -1. Sodium hypochlorite and calcium hypochlorite are powerful caustic disinfectant cleaners used in the home and hospitals. It has a bleaching effect. They stink of poisonous chlorine and can burn your skin. A particularly nasty radical called cyanide is formed when carbon and nitrogen atoms combine. Carbon is in group 4 of the periodic table and has 4 valence electrons shown in grey. Nitrogen is in group 5 and has 5 valence electrons. They share 6 electrons together to form a triple covalent bond. 2 are from the carbon, 3 from the nitrogen, and 1 from the element that the cyanide radical combines with. The 2 atoms each have complete shells of 8, a lone pair of their own, plus 6 in the triple bond. The cyanide radical is deadly. Eat its salts or breathe in hydrogen cyanide gas and your red blood cells cannot carry oxygen. You turn blue-black, a condition called cyanosis, and then die. Cyanide is sometimes used to recover gold from rock and is found in the seeds of wild almonds and apricot kernels, so be careful of your health foods. The carbonate radical is found in seashells, the limestones they form, in animal and human bones, and seawater that has not been made too acidic by fire-mad humans. Let's see how it forms. The oxygens have 6 valence electrons each and need 2 each from the carbon. The carbon only has 4 valence electrons, so 2 electrons are brought in from a metal atom such as calcium to satisfy the needs of the oxygens. So this is the structure, right? Wrong. The central carbon has only 6 electrons around it. It needs 2 more electrons and starts dragging in another lone pair from an oxygen to form one double bond. The problem is, which oxygen does it pick on? We know from measurement that this is a symmetrical planar molecule. Chemists call it a resonance structure. The single double bond flits around the circle with the 2 single bonds. The ammonium radical is unusual because it has a positive charge and is written at the beginning of compound formulas. It is found in natural and artificial fertilisers needed by plants to make protein. It has a tetrahedral structure where all the valence electrons are bonding. We add 4 lots of 1 electron from the hydrogens to 5 from the nitrogen to make a total of 9. It gives away 1 to fill nitrogen's outer shell of 8. The hydrogens are happy because they have full shells of 2. The nitrate radical is also found in fertilisers. It has a planar structure just like carbonate. The oxygens each have 6 of their own electrons plus 2 electrons shared in the single bond with the nitrogen. The structure requires 6 bonding electrons, 5 from the nitrogen and 1 from another element. Nitrogen still needs 2 more to fill its octet. So this is a resonance structure with a moving double bond just like carbonate. The phosphate radical is another fertiliser chemical with a tetrahedral structure. The oxygens need 2 extra electrons each to share with the phosphorus, making a total of 8 bonding electrons. The phosphorus has only 5, so this radical gains 3 electrons from outside, giving a net charge of 3-. The smallest element, hydrogen, needs just 1 more electron to fill its outer shell. It usually does this by sharing, even with itself, to form a molecule. The hydrogen ion is the most reactive. It has lost its electron and is effectively a proton, the second smallest charged particle after the electron. It likes to attach itself to lone pairs of electrons in existing ions to form new radicals. Here are some examples. Transition metals have overlapping outer shells. This allows them to provide several bonding electrons for oxygen to share. Here are two radical examples. On paper, write the names of the radicals in each of these compounds, plus their valencies.